We are now discussing about optimality conditions for minimizing a differentiable function over a convex set. We have spoken about a specific structure in the last lecture, which was this structure, and today we are now taking up the case when C is an open set. Now, consider a closed convex set with a non-empty interior, and if x bar is in the interior, then the normal cone to C at that x bar at the interior point consists of nothing but the vector 0. It's of course what is a normal. If a point is outside a set, it is normal to the normal means the difference between the vector x and its projection, x minus projection of x. But what is if the point itself is inside the set, then what is the projection point itself? So x minus projection x is 0 vector. So for x bar in the interior, it is, so a for any if is the 0 vector. So that's the kind of rough idea that you should have. Of course, you can say whatever it is in the boundary, because in the boundary there is always a point which is out. So you can always have a point which is outside the set, and that point on the boundary can be a projection to that point. But if I'm in the interior, I can always have a neighborhood which completely keeps me in the interior of the set, completely keeps me inside the set. So there cannot be any point outside to which this interior point is a projection. So so for any situation, it's always, there's no way you can get a non-zero vector, right? So that's the kind of thing. It will be always 0. Now, of course, there's a proof for this. The proof is very simple because it just applies the idea of what you mean by an interior point. If x bar is an interior point, then for any w that you take, you can move of any direction w. If you move very little along w, from starting from x bar, if you move a very little from that point, then for a sufficiently small lambda strictly greater than 0, I can still remain inside the set C, or because I'll still remain inside a ball which is inside a set C. That's the idea. So what would happen is that x bar plus lambda w would be in the set C, and what will happen is that in this particular case that V is in the NC x bar, so you will choose this particular element in C, and then you will get this equation. So this VW is less than equal to 0. So what does it mean? This is for any W that you choose in Rn. It doesn't matter what is the W. So you choose that, but when choose V to be W to be particularly V, you have norm V square to be less than 0, which means ultimately that norm of V must be 0 because V is always positive. So which simply means that V is equal to 0. It doesn't matter. So we have chosen V to an arbitrary element in NC x bar. So that's it. So any element is 0. So if C is a differentiable function, f is a differentiable function and C be an open convex set on Rn, and if x star is the local minimizer of f over C, then the gradient must vanish at x star. That is, x star must be a critical point of f. So this is a very important result. It tells you that from the point of view of optimality condition, there is no difference between optimizing over an open set or optimizing over the whole domain Rn. There is no difference, because you will ultimately lead up with the same criticality condition, that grad f(x) star equal to 0. Okay. So this may be it will give you one of the local minimas over. So of course you can say that, okay, there can be, when you consider Rn, there can be other local minima, of course, but at least one local minima would be captured here in this set C. So from a point of view of optimality condition, there is no real difference between these two. So here, but we have now, again, we have to apply the theorem that we know. But we have, suppose you take y to be in closure of C, because we talk about the normal cone on the closure of C, on the closed set. We will soon see that this forcefully keeping ourselves to a closed set while talking about normal cone is not really required, and we can broaden the definition. The issue is that we keep on taking it because the idea had come out straight out of projection, and the unique projection is possible when there's a closed convex set. So that because that idea has come straight out of the idea of projection, we are still continuing with the idea of uh, closed convex set being the real harbinger of the definition of normal cone. That is the theater in which this whole idea of normal cone makes sense. But actually, you can broaden the definition pretty easily. Yeah, and observe that now you take y to be in a closure of C. So there must be yn in C, means from the interior of the closure, because C is a convex set. The interior of the closure is the interior itself. So C itself in this case. So if so, there must be a sequence yn which converges to y. So now, because f is a continuous function, because it's a differential function, it must be continuous. So now for each of these yn, we have fin greater than fx star. So since f is continuous, because f is differentiable, so I have not written here f is continuous because it is differentiable, because you know that it's already given to be differentiable. So we will have fy is greater than equal to fx. So x star is also minimizer of f over closure of C. So I'll write minus grad fx star element of closure of C. Now, because C is convex, the closure of C is convex. And what does it say? So, but what is x star? X star is in C. So x star is in the closure of, x star is in the interior of the closure of C, right? So because of this relation that you have between in the case of a convex set. Of course, these relations need a proof, but they are not very but they're very intuitively, if you look at the picture of a convex set, they're very intuitive. So we are not getting into the proofs of those details. Maybe as I'm pulling the notes into a formal book or lecture notes, so that would have all these details given in already in the chapter on convexity. But this is something intuitive to you. So x star is now in the interior of the closure of C, because x star is in the in C, because C is here interior of C, because C is open. So which means what we have learned from the proposition before, that the normal cone to x star at closure of C is 0. So that simply gives me this condition. That's it. Now we are going to consider the special case where you have the non-negative orthant, that is C is equal to Rn. So that is a special case that we are going to consider. A special case. So we need to compute the normal cone at this point if I want to write down the optimality condition. Of course, this is a closed set. Now, sometimes we use the symbol, the vector x is greater than equal to 0 to mean x element of Rn plus, which means all the components xi's of the vector x, which is given by the component x1, x2, dot, 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 xn, all these n real numbers are non-negative, that is greater than or equal to 0. So basically, I'm trying to look at this problem, which I now call P1 hat, where my C is given by Rn plus. So of course, the optimality condition is this: minus grad fx star is element of the normal cone to x star, normal cone to Rn at x star, provided x star is not, I should write not minimize as f over Rn plus, but I should rather I think I wrote in a little hurry. I think I should write it as kind of, it is a local minimizer of f over Rn plus. That would be more correct. So how do we compute n of Rn plus? So that's the idea. So let us look at the picture where we'll take n equal to 2. So our C would be R2 plus. Now any point inside the interior, that is in R2 plus plus, that will have 0. That normal cone will be the trivial normal cone containing only the 0 vector. If it is not the trivial case situation, that is the non-trivial situations are at the boundary, which can be projection points. For example, if you take this part of the boundary now that is on the x-axis, take a point of the form x1 0 where x1 is positive and this is 0, then what would happen? You know what is the projection? It's a perpendicular. So here you draw a perpendicular line. But you know that these cannot be viewed as a cone because it's kind of a translation, because it's not a cone. Because if I take any vector here, because the vector would be vector position vector would be measured from the origin. So if I take any vector here from the origin, that when I pull it, it will go out. So basically the cone is here. So for any point on the x part of the boundary, the non-negative part of the x-axis, a y-axis, is the normal cone. Now if you take any point here where on the y-axis part of the boundary, first we took it on the x-axis part of the boundary, now we are taking on the y-axis part of the boundary. Of course, you can understand by the picture of the normal cone that you have seen in your last lecture, some old lectures, no, in this course, maybe not very old, maybe some 4, 5, 6 lectures ahead. So there you know that this set is nothing but a translate of this cone by an amount x1 0, right? Now here 0 x2, where x2 is the second y-axis, y coordinate is positive and the x coordinate is 0. So there this is the perpendicular. So the corresponding cone is nothing but the negative part of non-negative part of the x-axis. And when both the points are 0 0, then the normal cone, so 0 for 0, this is the projection. Take a point here, 0 is the projection point. Take a point on the non-negative x-axis, 0 is the projection point. Take a point on the negative, sorry, I'm talking about non-negative. I'm making a mistake here. Please understand. This part is the not non-negative. This, for example, here for x1 0, this part is the non-positive x-axis or negative x, non-positive y-axis or negative y-axis you want to call. So now for the part or of elements of the form 0 x2 where x2 is positive, the non-positive x-axis is the normal cone. Now when you have C is the element of R2 plus, all these points in the third quadrant are actually points of projections. For all these points, 0 becomes a point of projection. For example, if you take a point here, 0 is not the point of projection. The point of projection is here. A point here, the point of projection is here. The nearest point is not 0. But if you take a point here, there is no other point. This cannot be the nearest point. The distance is larger. 0 is the nearest point. So 0 is the projection point. So the third quadrant becomes the normal cone when both x1 and x2 are 0 0. So if we write it down, this is what it means. So it consists of all v1, v2, and v1 is 0 and v2 is less than equal to 0. Non-positive, that is actually this set. So it is 0 when both x1 and x2 are 0. And again, when you are having x1 is 0 and x2 is positive, you know what happens. It is this one, the non-positive x-axis. So you see the x part is this less than equal to 0 and the y part is 0. Here the y part, x part was 0, y part was non-negative. And when x1 is 0 and x2 both is 0, then it is minus R2 plus, which is the third quadrant. So once it is done, suppose I take f is from R2 to R2 be a differential function and x star be the local minimizer of f over R2 plus. Then the optimality condition is nothing but the partial derivative of f with respect to x1 and with respect to x2, both are non-negative numbers, each of them evaluated at the point x star. Again, what is this? This is nothing but the gradient can be written in this form. And this is the element of this normal cone. Of course, you can write transpose here to be much more correct in the sense, because if you take these as all only as column vectors, you can always write transpose. So what would happen? So you take these three different cases. when x1 star is 0 and x2 star is 0, then if these are elements of the normal cone, you must know what should be their signs. So when x1 star is 0 and x2 star is equal to 0, that is on the when it's on the x-axis part, then you know that we are looking at the part, we are getting the non-positive y-axis. So this part is 0, the del f del x1 is equal to 0 because it is the x part, and this part is non-positive, is negative, non-positive actually. So when you write down, this is what will happen. This whole thing will reverse when you talk about maximizers. So for maximizers, this would be less than equal to 0. So you can argue in the same way. Basically what you're doing, you're choosing the values of x1 star and x2 star, and then just looking at what you have here, you can immediately check for each one of them. For each one of them, you can check what is the situation. When both are strictly positive, these are nothing but 0. When the x-axis is 0 and y-axis is strictly positive, this is what you would have, and so on, and this is what you would have. So basically, instead of writing, we are just, you can just figure them out very simply. So summarizing the whole thing, this is what you have. So when it comes to Rn plus, then we can actually extrapolate, just push our imagination a bit from R2. So when you do push our imagination a bit, you will see the normal cone to Rn plus at any x is nothing but a vector w with a very interesting fact. If you look at it, look at this, there is an interesting fact that emerges here, and this is a very key fact of optimization theory which is emerging here, which is called the complementary slackness condition. What is emerging here? So here, when x1 is strictly greater than 0, the corresponding value of the normal cone vector is 0, and when this is only for Rn plus type sets and for R2 plus, and when x2 is equal to 0, then v2 is the corresponding part in the normal cone vector is less than equal to 0. So if the first quadrant of the vector where you are actually trying to find the normal cone, if the first quadrant, thing is strictly bigger than 0, you get v1 is equal to 0. If the second case, in the second case, if you have x2 equal to 0, then the corresponding v2 is less than equal to 0. So you have both x1 is strictly bigger than 0, x2 strictly bigger than 0, then you have the 0 vector. This I should have written as 0 0 actually. So both becomes 0. So here you see x1 is 0, then w1 is less than equal to 0. When x2 is 0, then w2 is equal to 0. Actually, you can write it as v1, v2 also, doesn't matter. So the same type of story will go on for this case. So in general, we can write n Rn plus x is equal to w with wi equal to 0 if xi is strictly greater than 0, and wi is less than equal to 0 if xi is equal to 0. So this thing which you will see later on can be expressed by the single statement that wi into xi is equal to 0 for all I. So hence, and when we are looking at the origin, n of Rn plus is nothing but minus. My normal cone to Rn plus at x is nothing but minus Rn plus. So in general, for the problem P1 hat in on Rn, this is the optimality condition that del f del xi, that all the component vectors of the gradient of f at x star is non-negative. That is, grad of f of fx is element of these things, this particular thing, right, is element of Rn plus. See, some of them can be 0, some of them can be, so they are actually in Rn plus in the case of minimization. But when you talk about a maximization, you will have the opposite. You will have this to be less than equal to 0. That is, the gradient vector actually would lie in minus Rn plus. Okay. So that's what is. When this vector, this del f del xi can be 0. Right. Del f del xi, if it is strictly greater than 0, then xi star definitely is equal to 0. So So whenever xi star is equal to 0, then del f del xi. So suppose here if xi star equal to 0, so del f del xi would be equal to 0. Strictly greater than 0, then del f del xi would be equal to 0. And so on and so forth. The same. So these are very complementary structures. So what does this mean? When I say wi, what does this two equation means? That both of them cannot hold with the strict inequality at the same time. If one of them has a strict inequality, the other will be 0. Both of them can become 0 at the same time. Both of them can hold with equality, but both of them cannot hold with the strict inequality at the same time. That is the meaning. That's the key idea in optimization, which we will very soon see. What is important now is to look into the situation when this function phi, when we are, instead of f from Rn to R, we take a function phi from R to R, a differentiable function, and then we want to look at the issue that we get when we maximize or minimize over a closed interval. Whenever we are having a function from Rn to R to R, our mind simply says, oh, differential function, you will just do f dash x equal to 0. But that's not the case when you come to uh, or when you put constraints. Because for example, you take fx equal to x square and take the interval 1 to 2, and you want to see the minimum value of this function over this interval. You know the minimum value is occurring at 1 and the maximum value is occurring at 2. So what do you take f dash x? F dash x is 2x, and if you put the value at x equal to 1, it is 2, which is greater than equal to 0. So on the left hand point, it is greater than equal to 0. So you can immediately understand that, because this is the immediately that f dash x equal to 0 story goes off. The constraint seems in itself intrinsically impose certain restriction where the standard norm rule would be invalid. So I'm just going to talk about what would happen suppose I'm looking at AB, where A is strictly less than B, so the interval is AB, A is on the left hand, and let x star equal to A be the local minimizer. Then what is the condition? And then we'll match with what we have come through this normal cone system. First we will do from the basic analysis in R, and then we'll go to the normal cone case, and we'll leave the rest of the cases to you to figure out, the students. And for the viewers for whom we'll not discuss all these cases in too much detail, the next part, so for them, they can obviously ask me for the notes. By now, I think most viewers who are viewing have figured out my email ID and all those things, so you can just do it. So let us consider the situation where at x equal to a, there is a local minimizer of phi. So at the end, if the minimizer is inside, then there is no problem. Then you know the answer. The answer is f dash phi dash x equal to 0. Phi dash x star equal to 0. But because the normal cone would be the 0 vector. But here we are at the end. So let us see if we combine our standard logic of the real line. So for h sufficiently small and greater than 0, if x is on the left, I can only move towards A. A is the left cornermost point. I can move only to the right. I cannot move to the left because I'm not interested in the values of x to the left of A. So to move right, I have to add a positive number to h. So once I do that, I know if I move a little bit, then phi of A plus h must be greater than phi A when h is sufficiently small, because there is a local minimizer. So phi of A plus h minus phi A by h is greater than or equal to 0, because this inequality is valid because h is strictly greater than 0. So I can divide by h on both sides, the inequality will remain valid. Now I'll take limit h going to 0 here, because h is positive anyway, it actually means h going to 0 plus. So basically I'm telling that the right derivative of a is greater than or equal to 0. But because the function is differentiable, so the right derivative is equal to the derivative. So phi dash a is greater than or equal to 0. Now by theorem 1, what we had learned in this discussion, all these 2 lectures, we must have phi dash a element of the normal cone to AB interval at A. And what is that? Because this is the interval, take any interval AB. So what you do, from you on the left hand side away, you just draw the ray starting from A to the left hand side, basically, which means you have drawn the negative part of the, or a non-positive part of the x-axis, which is nothing but minus of r plus. So which means minus phi dash A must be less than or equal to 0, which means phi dash of A must be greater than equal to 0, which exactly conforms with what we have here, exactly conforms with what we have from the basic analysis. So with this we are, so what would happen if B is the local minimizer, and what would happen if A is the local maximizer? You can do all kind of stories now, which we will not be doing. Uh, so we will in the next class talk about specific optimization models in economics, where C would be given by, as a special structure given by some inequalities and inequalities that we will keep in mind. But we will just look in focus on certain optimization models which comes in economics. We will not get into more details here, because as the time would run out. So we will instead of doing that, we will consist of those models, especially those models which involves inequalities as constants, where the constant set is defined by inequalities. So we will look into that issue, uh, and that will be our next discussion in the next class. For this class, let us say goodbye. Thank you.